Hello, and welcome to another episode of MAIN-iac Science Lab. I am Mr. Andy, Youth Services Librarian for the St. Johns County Public Library System here in St. Augustine, Florida, and today we're going to talk about light. But before we get to that, I want to show you some of the things you're going to need if you want to participate in our experiment with the program. We're going to do a couple little experiments, one big one at the end, but just in case you want to play along, go ahead and grab these items. You're going to need a little flashlight and some cardboard tubes. Not necessary to enjoy the program, but you can experiment along with me if you have these items. You will also need a glass of water, clear preferably. Works a lot better that way with light. You will also need a spoon. A silver one or metal of some sort. The shinier the spoon, the better. Make sure it's clean, make sure it's super shiny, because you're gonna need that shiny surface for our experiments. You will also need some sort of square edge. It can be anything. It can be a tabletop, it can be a box, it can be a windowsill, it can be the edge of your counter. But for my purposes, I'm using this little box. I'm going to show you what we're going to do with it so you can pick out the perfect edge for you to use as well. We're going to take the edge and we're going to put a piece of paper at the base of it. During the experiment, we're going to take that glass of water half filled and balance it on that edge. I'm only showing you this now because I want you to consider that when choosing the surface you're going to work on. You're going to have to be able to balance a glass of water on it. So that's definitely going to affect your decision-making process for what edge you're going to use. You're also going to need some sources of light. I have a large flashlight that I'm going to use, but unfortunately, this large flashlight, like most flashlights in most of your homes, is an LED light. And I'll explain why that makes a difference later. If you have access to an incandescent light, have one available. They're much better, but they're harder to find these days because everybody's going LED for energy saving. These are energy hogs, but they have a much brighter light spectrum. So I'll tell you more about that as we get into the program as well. So let me set my stuff aside so we can talk about light. So, light. MAIN-iac Science Labs. What is light? Well, the simple answer is light is energy. Yeah, it really is. It's a form of energy. And most of our light comes from the sun in the form of solar energy. Now, solar energy is generated by the sun and it travels to the Earth going a full distance of 93 million miles. Now, do you want to take a guess how long it takes to travel 93 million miles? If you were a light wave, that's right, 8 minutes. Wow, that's fast. 93 million miles in 8 minutes. It takes the average car on the freeway 60 minutes to go 1 mile, maybe a little more, maybe a little less, depending on the highway stretch and the speed limit and that stuff. But think about that, 60 minutes for 1 mile for a car, 93 million miles in 8 minutes for a beam of light. That's pretty fast. Now you know what they're talking about when they say something is traveling at light speed. Well, light travels in waves, kind of like sound waves do. They're streams of photons that have crests and valleys, just like a sound wave. And unlike sound waves, though, light waves do not go around things. They go in straight lines only, and they can be stopped by obstructions. Pretty cool. Well, think about it. If you want to have a dark room, when it's daylight, you have to obstruct the light with something. A blanket, a door, window shades, whatever it takes to stop the light from entering the room to make the room darker. You can actually do that. Now, if you close the door, does sound disappear? No, you can still hear it. It might be a little quieter, but you can still hear it. Light waves come to a complete stop when they hit an obstruction. And I've got a quick little experiment to show you to explain kind of how that works. Well, at least give you a visual representation of how it works. So that first little flashlight I told you about, here we go. You can see the light. I'm going to take one cardboard tube and I'm going to poke that flashlight into that cardboard tube. So, can you see the light? Yes, you can. Turn it off, no light. Turn it on, there's light. Now, if I take a second cardboard tube and I stick it to the end of that, you can still see the light until I bend the tube and the light is gone. It's still on, it's still there, but now it's gone. That's because light will not travel around corners. It doesn't do that. It only goes in straight lines. Light, bend the lane, no light, all gone. Pretty cool, huh? Yeah, that's what we mean when we say that light only travels in straight lines. It doesn't go around things. But light can be bent. It's true. And I'll explain to you how that can happen. Let's go back to our diagrams here. Let's see. Before we get into bending water, let's talk about transparent. Some things are transparent and light goes right through it and images can be seen very clearly. Water is transparent, well, when it's clean water. Glasses are transparent, windows are transparent, plastic sheeting can be transparent. Light goes right through it and you can see objects on the other side. This glass of water is transparent, but think about this. Light can be bent. When it travels through different substances, you might be able to see through that item, but it can still be bending the light just a little bit. And to do this experiment, I encourage you to grab that glass of water and your spoon. And I'm going to show you something really cool. So take your glass of water. There it is. See, you can see me through the glass of water. There I am. Hello, how you doing? You can see the stuff behind me, the door, etc. It's all there. It's not blocked at all. Take your spoon and put it in that glass of water and then hold it up. Can you see what's happening? It looks like the spoon is broken. You can see the handle going into the water, but then the spoon is detached from it. You see that? There you go. Look at that. How does that happen? Well, the light has been bent. What's happening here is light travels through the air faster than it travels through water. So what you're getting is refraction. The light is bent. It's slowed down as it goes through the water just enough to alter the image. Pretty wild, huh? Yeah. Refraction. When light travels at different speeds, it can appear to bend, because it kind of does. It slows down. So the light going through the air and the glass is going at one speed. The light going through the water is going at another speed, which makes that spoon appear to split underwater. Pretty fascinating stuff. So let's talk about some other light terms. Let's go back to my thingy here. Now, translucent is another term you may hear when talking about light. Light passes through something, but it's difficult to make out the details of items on the other side of that something. This jar of honey is a good example. You can see that there's light through the honey. You can kind of see a glow there, but you can't tell what's behind it. Can't really see what's behind it anyways in this picture. That's not a good image, but you get the point. If you were to put your hand behind that jar of honey, would you be able to see your hand? You might see like a blob, but you wouldn't be able to see the hand. That's translucent. Now, another term, opaque. Light cannot pass through objects that are opaque at all. If you shone a light at that coffee mug, and put your hand behind it, you would never see it. Only thing you would see is if you went around that coffee mug, you might see its shadow. Because what's happening is those straight shooting beams of light are shooting right at the mug, stopping when they hit the mug, but continuing around it on the sides. That creates the shadow. It's like a void behind the mug where light isn't. So you see a perfect outline if you have a strong enough light and it's dark enough in the area. Bright light comes from all directions, that kind of diffuses things a little bit. But if you're in a darkened room and you shine a flashlight at that mug, the only thing you're going to see is the shadow on the other side of that mug. You will never see through it at all. Light is stopped completely by that object. Therefore, that object is opaque. Now, some flat surfaces that are shiny can cause reflections. And the most common one we know of is a mirror. Now, what is a mirror? It's literally a piece of glass with something dark behind it. A sheet of plastic, a layer of wood, paint, whatever. That makes that more reflective because light doesn't pass through, light bounces back from that shiny surface. You can use a mirror as for reflections. You can get your reflection off of a shiny hood of a car or maybe a darkened window. Your cell phone, if it's turned off, the face of your cell phone has a mirror-like quality to it. It will reflect the images that are, opposite of it. You can even probably see an image on a super shiny apple if you try it hard enough. Now, that's where our spoon comes back into play, because if you find something shiny that isn't flat, you may notice the images are a little weird. Why is that? Well, grab that spoon again, and let's take a look at our reflection in the spoon. I'm going to stop this share so I can show you what to do. So if you take your spoon and you look at the bottom of the spoon, the round part, we'll call that the bottom of the spoon. Very scientific, yes. And if you look at that, you can see yourself in the image. But it might look a little weird, especially the closer you get. In fact, you should be able to see the whole room behind you, but the room may appear to bend some. If you bring the spoon closer, you may notice your head stretching, your nose and your eyes look kind of big, and everything else just kind of warps off into the background. Now, why is that happening? That's because the curvature of the spoon is bending the light. It's actually reflecting it in different directions is what's happening. So imagine you had a teeny tiny little ball, and you took that teeny tiny little ball and you threw it directly at the center of the spoon. That ball will bounce right back at you. Now, if you threw that same teeny tiny little ball at the outer edges of the spoon, which way would it bounce then? It's physics, right? It would bounce away from the center of the spoon. Well, light rays are doing the same thing. So while you're seeing the reflection, it's bending and warping as they bounce from the center of the spoon directly back at you. But as you go around that curve, they're bouncing away, which warps the image and stretches it out. That's how that works. That's how funhouse mirrors work, that kind of thing. Because they're curved and wavy, so the light rays are kind of going everywhere. So depending on where you are in reference to the curve, your face and your body will stretch in different directions as the light rays are bounced away. Now, take that same spoon, turn it around, and look to the middle, the bowl of the spoon. What happened to that image? Looks a little weird, doesn't it? Are you upside down too? I am. I am upside down in this image. How's that happening? You look at it this way, you're right side up. You turn it over, you're upside down. I don't understand. Well, I do, but it's easy to see why you wouldn't understand it, because unless you understand how light rays work, it wouldn't make any sense. Imagine that tiny little ball again. If you throw it at the center, it's going to come back. But if you throw it at the edges of the spoon, it's not going to bounce away. It's going to bounce back inwards again. So the light rays all around the outside of the spoon are bouncing inward to the center of the spoon again, causing the image to flip. Whoa! Light does some pretty interesting things, doesn't it? Man, oh man. Sometimes you think about it and it just kind of boggles the mind a little bit, but it's pretty cool and cool to understand and helps make sense of the world around you a little bit more when you see weird things, because it's all light making things happen and how we see those things. So what happens is the spoon has a circular curve. The bottom of the spoon, that technical term we're using, is convex, and it sends light rays away from the spoon. The bowl of the spoon, the middle part that you would put your cereal in, is concave and reflects light waves back at the spoon, thus turning the images upside down. So now that we've talked about how light waves move around, let's get into color. Yes, we see the world in color, don't we? How does that work? It's kind of wild. Well, we're not going to get too deep into color because that's going to be a very long subject. We're just going to touch on it a little bit. Pure light is known as white light, but it's not actually white. It appears to us to be clear, but there's a spectrum of colors within that light. Now, we see color because an object reflects certain light waves but absorbs others. That's how we determine, that's how our eyes determine what color something is. It's all getting hit by the same light, and all the colors are in that light, but the items change colors visually based on how it absorbs or reflects certain sections of the light wave. So let's say you have a red apple, for example. The red apple absorbs all the colors of the spectrum, but it reflects the red light waves. So we see that apple as red. A white sheet of paper reflects all the colors of the spectrum, every single one of them. So it comes out white. A black sheet of paper absorbs all the colors of the spectrum, absorbs everything, reflects nothing. Therefore, it appears to be black, and so on and so forth. Different colors appear to be different colors to us based on what sections of the light spectrum are reflected and what sections are absorbed. Pretty crazy, huh? Very interesting stuff to me. Now, if you have a prism, which is a triangular shaped piece of glass, there's a picture of it here on the screen. That's like an end shot. It's actually kind of a long rectangular, not rectangular, but triangular. It's a long thing. It's not just a flat one-dimensional. It's actually a three-dimensional object. But if you shine white light through a glass prism, it will split the light wave into the different colors of the spectrum. And there's 7 discernible colors, obviously with various fine gradations in between each one. But those colors are red, orange, yellow, green, blue, indigo, and violet. We learned those colors, I learned those colors when I was a kid by remembering the name of the guy, Roy G. Biv. He will always go down in history as the color guy because his initials spell red, orange, yellow, Roy, G, green, and Biv, blue, indigo, violet. Roy G. Biv. I don't know why that was so easy to remember, but it worked. So teachers used it for a really long time. Do they still use it today? I don't know. Are you in class? Maybe ask your art teacher next time. So what's going on here? Basically, different colors of light travel at different speeds through the prism. As it enters the prism, travels through it, and then exits it, they're going at different speeds. And by doing that, they're split out of the spectrum. Now, different colors of light have different length light waves. So they can be easily split when going through something like a prism. Kind of like that water refraction where you were looking at the spoon and the water in the air is one speed, and the water in the glass is another speed, or the air through the light through the glass is a different speed than the light through the air. It's kind of the same way with a prism. So you can see mathematically, if you were to take a ruler and measure the distance the light travels through that triangle, you can see the red travels through a much shorter distance through that piece of glass than the violet travels. By they're going at different lengths of distance through the glass, altering the speed that it travels, that's how the light is split up into a spectrum. And I don't have a prism. Odds are you don't have a prism, but it is possible to make a prism at home. Not a perfect one. Obviously, one of these works way better because it's a very fine, measured out piece of material, but you can make a prism and make a rainbow with a source of light at your very own home. And I'm going to show you how to do it. It's pretty easy, also pretty tricky at the same time. So you might take some experimenting, especially since different light sources have different light spectrums and different rooms have different amounts of light. There's a lot of variables that can go into this, but this is science, so we're going to experiment, and I'm going to show you how. I'm going to set up the experiment on my tabletop here so you can see me setting it up so you know kind of what to do. And I'm actually going to run through the experiment. The problem is, due to technology and cameras, you're not going to be able to see the light changes. So I'm going to run through the experiment one time in this mode, and then I'm going to go through the experiment a second time with my cell phone recording it, because I can get a lot closer to the light source so you can actually see the color spectrum up here, okay? But when you're doing it at home, you don't need a camera. You can just watch it happening on your sheet of paper. So I'm going to show you how it's done, and then I'll do it again so you can actually see it happening, okay? So bear with me. This is where your sheet of paper comes in handy because you want a clean white surface for your light spectrum to spread out on. If you do it on different surfaces, it might come out a little bit differently. This is light we're talking about, and reflection and absorption and all that stuff. So take your edge. I'm using this square box because it's fairly flat, and I can balance a glass of water on it without too much concern for spillage. You're going to take your glass of water. It's a little full. I'm going to drink some of that. Hydration is very important. And you're going to balance that about half on, half off the box. But be very careful because it's tippy. You don't want the water to spill and ruin your experiment. So it doesn't have to be 50% on and off. It has to be just a little bit off. And keep in mind the glass that you choose, because if it has a lot of gradations between the thickness of glass, that's going to affect your experiment. It's not going to ruin it. It's just going to affect it. So keep those variables in consideration. As simple a glass as possible would be ideal. Less gradations of thickness, because that definitely affects the travel of light. And a fairly dark room helps, but it's not really necessary because you're using a strong beam of light from your light source. So what you're going to do is you're going to take your light. I'll start with the flashlight because it's easier. You're going to turn it on, and you're going to shine it directly into the glass. And you'll already start seeing the flashlight beam going through the glass and onto your sheet of paper. Now, depending on the type of bulb inside your glass, you're going to get different, inside your flashlight, you're going to get different results. So bear that in mind when doing your experiment. But as you go down the glass, go like this, and try to shine directly at the edge of your surface through the glass. And as you bend down, you should see the light pattern changing on your sheet of paper. And if you bend it just right, a rainbow should appear. And that is the color spectrum being spread out through your homemade prism. So right now, I can see a rainbow on my sheet of paper. You can't see it because the camera on my computer is not strong enough to recognize that light change, which is unfortunate. But I'll show you this in a minute with my cell phone because I can get a lot closer so you can actually see the color change. Now, I mentioned earlier that doing this with LED light, there's that rainbow. I wish you could see it. You will, don't worry. I'm going to show you. In my research, I discovered that LED light sources have a very different color spectrum than incandescent light sources, or the old-fashioned light bulbs that have the little filament inside of them, the Edison-style light bulbs. Well, that is a result of technology, because LED lights are way, way, way more energy efficient. And you can run like 100 of them for every one incandescent light bulb and use the same amount of energy. Now, that's a made-up number. It's not a precise figure. You can research it if you need to know the precise figure, but it's just a generalization to give you an idea of how LED versus incandescent. So 95% of light bulbs on the market these days are LED, and probably most of the ones in your home are LED. But if you still have some old flashlight laying around or some old-fashioned lamps that have incandescent light bulbs in them, you're going to get a very different experience because of the color spectrum. I didn't get an image of the spectrum difference, but LED light puts out way more violet, green, and yellow, where incandescent has a much broader, even spectrum. So a lot of the red and the orange and some of the other colors are suppressed in an LED system. So you're going to get a slightly different rainbow. It might not be as intense or as visually apparent. You'll see color changes occurring, but you'll definitely see that some of the colors come out stronger than others. Where with an incandescent light, you can usually get a little better visual of a rainbow. So at this point, I'm going to go ahead and switch over to my camera phone so that I can show you light gradations. Because you've got to get a little closer to make it work. Now, as you can see, the room that I'm in has natural light. You can see it reflecting off my hands. It's pretty bright, which that's okay. The experiment still works. So you don't have to be in a dark room, although if you are in a dark room, it might be a little more dramatic because you don't have all the external diffused light interfering with your attempts to make a rainbow. So it's up to you. You don't have to do it in the dark. It doesn't really matter. You can still do it with your strong light source. So here I go. I am recording on my phone. See, fancy little phone. So I can get a lot closer so I can show you the rainbows. And I will splice this in. Why am I telling you my studio tricks? Just watch this.
Okay. So I've got my sheet of paper. There's my glass, my sheet of paper. And I'm going to start with my flashlight. So there, you can see the light coming through the glass. It's pretty white, maybe a little bit of blue. But as I go down the glass, you should be able to see colors emerging. There it is. There's our rainbow. See those colors? Oh, I touched the glass. Be very careful not to touch the glass when you're doing this, because you can set your water moving, which makes your prism rock and roll. Look at those colors coming out. We're making a rainbow. It's not as clear as I'd like it to be, because we are working with cell phone technology here. But when looking through it with your eyes, you can see the color changes a lot better. We just made a rainbow using just a glass of water and an LED light. How cool is that? So see if you can do it too. Now on mine, I'll see if I can show you. My flashlight has actually 3 light sources in it, which makes the experiment a little trickier because you're actually making 3 rainbows at one time. That's a little odd, but that's the flashlight I had to work with. My other flashlight that I had has like 1, 2, 3, 4, 5, 6, 7, 8. It has like 9 light sources in it, which made it about impossible to do this thing. So try to find one with a single light source if you can. But as you can see with mine, it has 3 in there. It still works. I'll do it again. We're going to put it straight into the glass. We're going to shine it over the edge. And then as we slowly, see I'm slowly moving the light down, you can see the colors emerging as the water and the glass are splitting the color spectrum up. See that? How cool is that? Super cool. And if you look really closely, you can even see the individual light bulbs appearing in there. It's kind of funny. Okay, cool. That's the LED version. Now we're going to do the same thing with our incandescent light and see what the difference is. It's definitely very different from the viewpoint of your eyes. It may not appear quite so different on the viewpoint of my cell phone camera because it doesn't work quite as well as the human eye does. The human eye is an amazing camera. It can see very, very fine details from natural light sources. So here we go. I got this guy here, shining it through. Let's see what our rainbow looks like. It's already, you can see it's a much bigger spectrum here, a wider spray of light. And we're going to start bending it through. Oh, there's that rainbow. Look how beautiful it is. Now, like I said, it has, oh man, that is so cool. And the way you turn it and bend it really changes things. It all depends on your glass. That's a very distinct rainbow right there. You see that? You can see the oranges and the greens and the yellows and the violets. It's beautiful. It all has to do with the angle that you're aiming at the water across the edge of your surface. See, right now I've got it almost like that. So you can see that is the way I'm doing it to create this amazing color spectrum, which, believe it or not, looks way better in person than it does on the phone. Okay, I've lost it, so now I'm just going to readjust slowly. See if I can bring it back. Oh, I lost it completely. Let's see if I can let's just start over. Winding it down. There it was for a second. Oh, see, it keeps coming and disappearing, that little rainbow. But as you move, it comes back. And it's all dependent on the angle that you're holding the light through the water across that edge of the surface. So we're getting a lot of the oranges and yellows. Let's see if we can get a full rainbow here. There's a bigger one down there below. It's tricky, and it takes some experimenting, but if you have the patience, you can absolutely make this happen. Man, I had it so good for a second there, and now I'm losing it. Let's reset. Slowly move down. You can see the colors shifting. See, this is where a glass prism works much better because the glass prism is a very measured product. You have a moving glass of water. There's kind of a rainbow there. There it is. There's the rainbow. Oh, I touched the box and now the water's shaking. And that is a hazard of doing it this way because water moves. A glass prism doesn't move. But there we go. There's our rainbow. You can see all the different colors coming through. And I touched the box again, made it all shaky. Let's see if it settles down. That is so cool. So now oh, look at that. It's beautiful. Now you know how to make a rainbow using just a glass of water
and a flashlight. How cool is that? Got you a quick glimpse of my camera setup. So that's all there is to it. And then if you see a rainbow in the sky, that's happening because of sunlight reflecting off of water moisture or water droplets that are in the air, which is really kind of cool. So that's how that works. So we've explored a little bit about light today. I hope you learned something, and I hope you had fun with that experiment making rainbows. I could do that for hours, just making the color changes on a sheet of paper. So cool to me. And I hope you enjoyed it, and I hope you learned a few things. Now you know how to make your very own rainbow. And that's about all we have for today. So for MAIN-iac Science Labs, I am Mr. Andy, and I'm happy to see you guys and can't wait to do another experiment with you soon. Keep an eye on the web calendar. We will update the progress on the next experiment as soon as we are ready. And for St. Johns County Public Library System here in St. Augustine, Florida, I am Mr. Andy, and I say good day to you, and I hope you have a wonderful rest of your evening.